Welcome to the AP Calculus BC video for skill number 212 and 213. I can identify discontinuity types and types of continuous functions, and I can also use limits to prove continuity. Featured to the right, trivia question for the video is what? Alright, so we'll start our notes on page 213a. A function f is considered continuous at the number a if the limit as x approaches a of f of x is equal to f of a. Very loosely, if you thought about that graphically, if the left-hand limit, we'll say of this point, if the left-hand limit is the same as the right-hand limit, is the same of the value of the function there, it is considered to be continuous at a. So I wrote that out alternatively, the limit as x approaches a from the right side equaling the limit as x approaches a from the left side equaling the function at a, and it's considered continuous. If that's not true, we have a discontinuous function, and there's three types of discontinuous functions. There's the removable discontinuity, which is a hole in the graph, and it includes a hole where you jump up to a different location. We also have the infinite discontinuity. These are where you have the vertical asymptotes and the graph is getting ever closer to the asymptote, and you can have a value within the asymptote. That's called an infinite discontinuity. Some textbooks and online you might see that referred to as an essential discontinuity. And then we also have a jump discontinuity, and that's where you're moving along your function and then you jump up to a different location and jump up a different location. So it doesn't have to be one of these stair functions. It can just be a lot of the piecewise functions show a jump discontinuity. All right, example 1 is asking us to show if the given function is continuous at a and the type of discontinuity if it is discontinuous. So what we have here is a piecewise function defined for when x is less than 1 and when x is greater than or equal to 1. And we're looking for the continuity at 1. And this is pretty commonplace where you're talking about continuity at the break between your two pieces. So if we're going to do that, we want to assess the limit as x approaches a from the left-hand side. So a left-hand limit, which would be our first piece. So we can evaluate the left-hand limit for 2x plus 3, and we find that to be equal to 5. And then we'll do the right-hand limit for our second piece, and we find that to be equal to 4. Because these two limits do not equal each other, we can immediately state that they are discontinuous, or that the function is discontinuous at a equals 1. A quick graph will show us that, in fact, we do have a jump discontinuity for that function. The second part of example 1 is another piecewise function where I've defined the function to be the absolute value of x minus 2 if x is greater than 2, and the negative root 4 minus x squared if x is less than or equal to 2. So we're going to do the same thing for a equals 2. So we'll assess for the right-hand limit, which will be the top equation. We're approaching 2 from the right-hand side, and we find that in this occasion the function is valued at 0. The limit of the function is valued at 0. When we approach a from the left-hand side, we're doing the negative root 4 minus x squared. We find that to also be 0. And finally, we evaluate what is the function at the value of 2, and we find that to also be 0. Because all three pieces are 0, we can say that the function is continuous at a equals 2. A quick sketch of the graph shows half of the absolute value and a semicircle, and we have a continuity that's occurring right at 2, 0. well, it's continuous for the whole thing, but that's the part we focused on. Another type of question would be showing that a function is continuous on an interval. And what this is saying is, for all of the values from -3 to 3, is the function continuous? So what we want to do is we want to find the limit as x approaches a of f of x for the function, and so we evaluate that. We use our limit laws to say that we can put the limit inside the radicand and take the limit of 9 minus x squared, and we find that to be 9 minus a squared, which happens to be the same thing as f of a. So we have proved that at the very least it's continuous from -3 to 3 exclusive. Now we should check the endpoints. So we're checking first a right-hand continuity. So we're approaching -3 from the right side, and we plug in, find the limit, and we find that the limit of that is 0, which does equal f of -3. So the function is continuous from the right at a equals -3. And then we want to see if the function is continuous at +3 from the left-hand side. So here we have our curve, and here is -3. We proved it from the right-hand side, and now for this part, we're proving at 3 from the left-hand side that it's continuous. So we take the limit as x approaches 3 from the left-hand side, and we get a value of 0, and that is the exact as the value of f of 3. So we have now proved that it is continuous from the left at a equals 3. So we have inside the interval, we have the left endpoint and we have the right endpoint. So the function is continuous on the whole interval. All right, wrapping up the ideas of continuity is this concept: if you have two functions, f and g, and we know they are both continuous at a, and c is a constant, then we can say the following functions are also continuous at a: f plus g, f minus g, your constant times f, f times g, and f divided by g, provided g of a is not 0. So if graphically, if you were to think about that, we'll say f is continuous at a, and g is also continuous at a. Then we can do the operations and say f plus g or f minus g, etc. is also continuous. It's important to know that there's several continuous functions or functions that are continuous within their domain. All polynomials are continuous, and since their domain is all real numbers, you could say polynomials are continuous on all real numbers. There's also rational functions, root functions, trigonometric functions, inverse trig functions, exponentials, roots, and logarithms. Those are all continuous in their domain. So we use that for our final example, example 3, that asks us, where is f of x equals root x plus arctan x over x squared minus 9 continuous? So using our properties from above, we are going to break this down. First, we look at root x, and we know that that is continuous on x is greater than or equal to 0. So at the very least, our whole function has that continuity. Arctan is continuous on all real numbers. So right now we're still limited to x is greater than 0 for our continuity, because the sum of those two shares the continuity of the most limited one. And then the final one, 1 over x squared minus 9, is continuous except at plus and minus 3. So what we have is a continuity that goes from 0 to 3 and 3 to infinity. And you can check that out if you wanted to graph that function. You'll see that it's continuous except at 3 or below 0. All right, this concludes our video for skill number 212 and 213. I can identify discontinuity types and types of continuous functions, and I can use limits to prove continuity. And the answer to the trivia question is, featured to the right is a pack frame.